Okay, it's 4 o'clock, so let's get started here. Project number 5 is due now. For some reason we're unable to turn it into me, please contact me after class. Final exams coming up. That's the last big grade that we'll have. It's scheduled for Tuesday of finals week at 1 p.m. Regarding the final exam, there's actually a take-home problem with it. And it's available on the test web page. You can download it right here. This I did recently update the format sheet notation summary. I finished writing the final exam a few days ago. And this is what the take-home problem looks like. Okay, now I have actually given this particular problem before with this class. So if you happen to have somebody else's stuff from previous people taking this class, please don't look at what they did for their answer. So it's just 10 points out of 100 total for the final. And it's based upon, I guess, something that occurred to me late summer 1997, early fall 1997. That summer I had spent it out in Idaho Falls, Idaho. I had an internship at the Idaho National Laboratory out there. And when I came back, actually home in Omaha, in mid to late August, I got to my parents' house. That's my official residence. And on my bed there was my mail that my parents had opened, and I wish you would have, because there had been this letter there for a few weeks saying that I had won this scholarship, the Ellis R. Ott Scholarship. For those of you who remember Michelle Quinlan in our department, graduated a few years ago. She actually won the same scholarship as well a few years ago. Anyway, so I won the scholarship, and the news that I won the scholarship got out at K-State, and eventually the student newspaper interviewed me for an article about the fact that I won the scholarship. And the reason why I bring this up is because while I was interviewed for this article, the reporter said, "Well, where are you going to do your dissertation on? Where are you doing your research on?" And this was I was just beginning my 4th year in the stat program at K-State. At least for K-State, students didn't really decide who they were going to do their dissertation with in terms of advisor or even a topic until late the 3rd year, beginning of the 4th year. So I had kind of a general idea, but I hadn't fully decided yet. And I said, well, I'm going to be working on something called the Bootstrap. So the reporter asked, well, what's the Bootstrap? So I explained it to her. I explained it to her correctly. This is what she said about my dissertation and the research I'm going to be working on in the article. I will read it to you. Builder will write his dissertation on bootstrapping, which is the application of the confidence interval on random samples and the assumptions made about the population from these confidence intervals. Okay. Now, this reporter, she had taken basically set 218, our equivalent was set 218 here. That was her only stat course. She was an undergrad. And with the help of this article, especially focusing on that particular paragraph, the article's on my test web page, answer the following questions. Number 1, did the reporter describe the bootstrap correctly? Please explain. Number 2, if you had to briefly explain the bootstrap to a daily Nebraskan reporter, meaning someone who has a very limited stat background, let's say just stat 218, how would you do it? Give me 1 or 2 paragraphs. Number 3, now put yourself in the reporter's shoes. How would you explain the bootstrap to the readers of the Daily Nebraskan? So let's say that you were actually writing the article. How would you explain the bootstrap in that 1 paragraph? So only write 1 paragraph. Now just remember that the readers of the Daily Nebraskan might even have a smaller stat background than this reporter did. They might not even have had stat 218. So this is I like this problem. This is the reason why I've given this problem a number of times in the past, because it kind of just sums up some of the stuff that we've been doing in the semester, but explaining it in a way that non-statisticians need to be able to understand it. Especially if you end up doing consulting in your career, you're going to need to do this kind of stuff. Okay? So, this is simply take-home problem for the final exam. Please have it emailed to me before you actually take the in-class portion of the exam. Now, I will admit that this article here, I find it very funny. Okay? And read the article. I think you'll get a general sense of what I mean, and especially if you take in my Stat 875 class, you're going to see some reference to my field goal kicking paper in here. I find it funny because the reporter, and maybe her editor really edited it really poorly, but the reporter has some quotes from two individuals that she also interviewed for the article, specifically Tom Logan, who was my advisor at K-State, and also Chris Malone, who some of you met a few weeks ago when he came and visited our university. And he has, and she has some quotes here from these two individuals, and they just don't fit very well in the flow of the text. Every time I read this article, I laugh. You can laugh too. But the thing, I guess, keep on going here. When this article came out, though, again, I was in my fourth year, my last year of taking classes. I'm going to probably start my dissertation research soon. Still need an advisor. And here I have this reporter, basically saying what I thought the Bootstrap was. I was kind of scared. Fortunately, Tom Logan still took me in as a student. Anyway, so.
Didn't want the misquote against you.
Yes. Especially with how she put his quotes in there too. Read the article. Okay, so are there any questions about that or anything else? Yes.
So besides the take-home portion, is the final exam fairly cumulative, or is it mostly focused on Chapter 6?
It's cumulative, but there will be more of, I guess, a tilt towards Chapter 6. If I remember right, I'm going to say 50 points out of 100 is Chapter 6 stuff. And, you might think, well, geez, that's a lot if it's a cumulative final, but if you put it into the context of Chapter 6 and the number of days that we'll spend on Chapter 6, and the overall grade then that Chapter 6 contributes this semester, since there's no project, it actually ends up being, Chapter 6 is actually weighted less compared to the other chapters.
What about the parallel processing and stuff you have on?
We'll see.
Okay.
We will do it.
Well, but will it be required?
We'll see.
Okay.
I don't want to make a commitment yet. Okay? So yeah, after we finish Chapter 6 here, we'll do this parallel processing stuff. And also we got, obviously, evaluations too. Okay, so are any other questions? Okay, so we left off on page 642. We were talking about a particular hypothesis test for a regression model. Where we're testing the slope parameter. Is it equal to 1 or is it greater than 1? And why our response variable was some return of a stock, active stock. And the independent variable or explanatory variable, predictor variable, or just call it X, was the market return. And in a corresponding regression model with this Y and X, we want to check the slope. Now we talked about how to do this using case-based resampling already. Now we're going to talk about how to do this with model-based resampling. Just to review how we would do model-based resampling without doing a hypothesis test. Let's discuss this. So we could say step one would be to, let's say, estimate expected value of y is equal to beta 0 plus beta 1 times x. So estimate that particular model so that you get beta hat 0, beta hat 1. You get your residuals as well. You get your modified residuals. Remember what those are. It's E sub j over 1 minus h sub j squared root. H sub j is the j diagonal element in the hat matrix. Okay. Now, once we have that, then, we need to form our resamples. With model-based resampling, we always keep the exact same x's. Okay, so we keep the design, you can say, fixed for every single resample. And so what actually we need to get is this yj star, let's say. And we set that equal to beta hat 0 plus beta hat 1 times x sub j plus epsilon j star, where these epsilon j stars are resampled from our mean adjusted modified residuals. Okay. Now let's talk about how we do this then for hypothesis. So again, we have to resample under the null hypothesis here. And I'm actually going to deviate a little bit from my notes because I think it's a little bit easier to do it this particular way. You get the same answer than what my notes focus on, but I think it might be just a little bit easier to do it this way. So step one, we need to estimate model under HO. So now we have expected value of y is equal to beta 0 plus 1 times x. So in this case then, we're going to get beta hat 0. You won't have a beta hat 1. We can still get a residual, and we can still get the modified residuals. Then, step 2 here, to get the y star j's, we'll do this. Y star j is beta hat 0 plus 1 times x sub j plus epsilon j star, where again we take the epsilon j stars from our mean adjusted modified residuals. Now, these mean adjusted modified residuals are of course different than when we were not caring how we were doing the same. Then, step 3, we want to estimate then the full model here, where we are actually estimating beta 1. Oops. So in other words, now with this resampled data, we have the y, j stars, we have our original x's. Estimate that model, so include the slope. And so from that, then you'll get a, for example, beta hat 0 star. You'll get a beta hat 1 star. You could get also, let's say, the square root of the estimated variance star of beta hat 1 star. And then you can This allows you then to get the distribution of the beta hat 1 stars, or equivalently, let's say the z sub 0 stars, by finding a standardized value, and use that as a reference distribution to compare either beta hat 1 or z0 itself. Okay? So that's the steps. Let's talk about how we can do this in R then. Now, on the top of page 644, you're going to see this set of code. This code works, but you can actually simplify it a little bit by removing that 1 plus. You get exactly the same answer, but the 1 plus is actually not needed. Now, in the step 1 that I had laid out, we need to estimate expected value of y is equal to beta 0 plus 1 times x. This is how you do it in R. Use the LM function. Here's my y, acme, tilde. Now, I don't want beta 1 estimated. This is how you can do it. Say offset market, where market is my x. If you've never heard of the term offset before, what that basically tells, it's actually a term that's used outside of just R itself. But here what this tells R is to include x in the model, but don't estimate a beta for it. Okay? Don't estimate a beta. By default, R will still estimate beta 0. So the 1 plus there actually told R to estimate it, but it wasn't really needed, because it would always do that unless you told it not to estimate the interceptor. So again, what's happening here, that first set of code, it is actually, get my toolbars out, is estimating this model. Okay, so I can get my residuals, get my modified residuals, get my beta hat 0 from this information. Then I need to go in my code here. This has been added to my program online. So here's the exact same code that we just saw in the notes. So here are my y hats, you could say. Again, these are basically beta hat 0 plus 1 times x. Then this is this is also in the notes. I could also get my hat matrix diagonal values as well. And you'll notice that they are all equal to 1 over n. Why? Well, if you actually look at the hat matrix here, we essentially, since we are not estimating anything for beta, we only have, in our x matrix, we only have a column of 1s. That's it. So again, we only have a column of 1s in our x matrix. So the only thing we're estimating is beta 0. So if you do the x times x prime x inverse x prime, you will notice that everything simplifies down to 1 over n times a matrix J, where J is a matrix of 1s. So on the diagonal, you always will see 1 over n. And so that's why you have 0.016 there. Okay. So this is not in the notes now. If I want to then find my modified residuals, then I just take my y minus the corresponding y hat divided by square root of 1 minus that hat matrix diagonal value. And this is what I get. So then what I would like to do is write a calc.t function, like we've done in the past, that calculates for me beta hat 1 and also the corresponding standard error for beta hat 1. My function is going to be calc.t.modBase. I'm going to pass in r sub j minus r bar have my usual indices. I'm also going to pass in my mu hat under HO, which, although I haven't actually defined it here, it simply will be this. And also I need to pass in x. So let's take a look at the actual function itself. So my data is basically these, the mean adjusted modified residuals. I put those into epsilon, the resampled values. I find my y. So what this is essentially doing is this right here. I now estimate my model to the full data. So this is why I needed to pass in x. I summarize the fit, and the reason why I'm doing that is so I can pull off a particular standard error from the summary output. And also I pass back my beta hats. So let's run it. And this is what we get. Now I can actually do the bootstrap. So I do it just like how we've done before. Nothing really new there. I put the results in boot.res.modbase. Notice I take the mean of all my beta hat 1 stars, and notice it's about 1, which is what we expect since we are resampling under the null hypothesis for this particular model here. We're working with y and x together. I can also then find my Z0 statistic. Simply, just make sure this is clear. Z0 is equal to beta hat 1 minus the hypothesized value of beta 1, which would be 1, divided by the square root of the estimated variance of beta hat 1. Note that I did not pull out values from my boot.res to do this calculation. The reason being is because, remember, we're passing in the mean adjusted modified residuals, so we won't get exactly the same beta hat 1 as what was observed. So that's why I didn't do that. My Z stars then, beta hat 1 star. Here is basically my standard error, calculated out for every single resample. And if I look at then the proportion of these Z stars that are greater than Z0 itself, I get 0.29. That's my p-value. Before we had a p-value of 0.277 with case-based resampling. Okay, real briefly, I'm going to go back in the notes. On the bottom page 642, I just discuss a little bit of a different way to do this, and that is, I say, well, let's find adjusted response values where I take into account that this beta is a constant, x is a constant, and I find y minus beta 1, 0 times x, in other words, 1 times x, and now that's my adjusted value. And essentially, it's adjusted response, and I can fit a model to that to estimate beta hat 0. Essentially, this is what this offset code does. It says, okay, now I have these constants here. Let's adjust my response now for these constants that are actually on the right-hand side of my model. And so I just took a little bit of a step out. And so I go through some of the details of if I would have done it my original way there. You'll get the exact same answer. And we can do just our standard plots that we normally see. So let's graph all the Z stars. So I have a histogram, normal distribution approximation on it. Green line is the observed test statistic value. You can see, obviously, it's kind of in the middle of the distribution. That's why our p-value was large. And we can see normal distribution approximates it well. Okay. Are there any questions? So section 6.2.6 now talks about what happens if you have non-constant variance. take a look at that on your own. You are not responsible for it. But it does have an interesting name for one of the bootstrap methods discussed called the wild bootstrap. Let's go to page 648. Now let's talk about multiple linear regression. How can we do that? You know, it's just easy to start with simple linear regression at the beginning. Now let's do multiple. So just review. You know, this is what your model would look like in a multiple linear regression setting written in the matrix form. Y is equal to x times beta plus epsilon. So notice the X matrix is the thing that's bigger than what it was before, and of course we have more betas. Epsilon itself is distributed in normal 0 sigma squared I. Of course, beta hat itself is x prime x inverse x prime y. Our variance of the beta hats is the estimated variance of the beta hat vector is the MSE times x prime x inverse. Remember, our book likes to use s squared as MSE. And I would normally call that var hat, beta hat, because it's estimated variance, but they don't. I normally, like when I teach regression analysis, I would say var beta hat actually sigma squared x prime x inverse. But I think in the context of what we're doing, it will be clear what the book means. You could also derive empirical influence functions, the non-parametric delta method estimate of the variance of the beta hats as well. Don't worry about that. It's not worth our time since we have very limited time left to go. How would you do model-based resampling? As you might expect. Notice my Y star here is exactly the same as before, but now I have extra beta hats and extra x's to worry about. Okay? Case-based resampling. Well, now instead of having y and x together, now you have y and x1, x2 down to x and p minus 1. What's difficult, or what can be difficult, is now hypothesis tests. So we're going to spend a lot of time on this. So this is page 650. So, you know, what you've seen in the Stat 870 or Stat 970 class is you often frame hypothesis tests in a multiple linear regression setting into a full model versus a reduced model. Or instead of a full model, you might call it a complete model. And so what we can do here is our model y is equal to x times beta plus epsilon. We can partition it up where I take the first, let's say, q plus 1 columns of x, take it times a vector, we'll call it x0, take it times a vector of alpha, which is the first q plus 1 betas, you could say, and take the last then set of columns of x, called x1, multiply it by a vector gamma, which is all the rest of the betas. And what we like to be able to do is actually test, is gamma, this vector gamma, equal to 0 or not? So the full model is y is equal to x times beta plus epsilon. The reduced model is now without x1 and gamma, because gamma is equal to 0. Let's look at a simpler case first, where let's say gamma is just a 1 by 1. So we're just testing one parameter, the last parameter given in our model. How do we do this with model-based resampling? It's the same idea as what we've done before. Y star is now equal to, you estimate the model under the null hypothesis, get the estimated values, call these mu hats, and you put them in here. These epsilon 0 stars then are resampled from your mean adjusted modified residuals, where again these come from the null hypothesis. I just put zeros there to emphasize the null hypothesis. That's how you get your Y stars. Once you get your Y stars then you fit the full model. So it includes then the corresponding variable that you're testing, the corresponding parameter that you're testing. You fit the full model to the Y star and axis data. So just like what we just did, except for now, we're not testing beta 1 equal to 1. We're testing beta 1 is equal to 0, so you don't have to worry about an offset at all. But you're fitting the model that contains the variable that you're actually interested in testing. So what you can do then is calculate the usual kind of test statistic then for every single resample, just like what we did in the previous example. So you can calculate what would be gamma hat star for this particular case, or your last beta hat, you can say instead. Form a t-test-like statistic to do the test. Case-based resampling is unfortunately much trickier. The reason why it's more difficult is that we need to account for the fact that there are these other variables in the model that we want to be in there, that we leave in there. And so that really complicates then how we can do case-based resampling. And what we have to do, though, is that the stuff that remains in your model, it's not being tested, it's an X0. We need to adjust for the effects of the stuff that's in X0. We need to adjust Y for those effects. But also we need to adjust X1 itself, what we are actually testing, corresponding parameter that we're actually testing. So this goes back a little bit to a discussion that we had in Chapter 4 when we were talking about partial correlations. And how do you remove a particular linear effect from both a response and a set of other explanatory variables? This is closely related then to what you would learn in Stat 870, where you talk about partial regression plots or added variable plots. It's the same basic idea. And so, first of all, to remove the effect of X0 from Y, simply estimate a model that has Y as the response, X0 as the predictors, or explanatory variables. Get the residuals E sub 0. What these residuals represent is simply Y without the, where I've now removed any kind of effect that X0 has on the model. So this is what's left over. But now also I need to remove the linear effect of X0 from X1. So how do we do that? Now take X1 as the response and X0 as the predictors or explanatory variables. So again, what this is doing is removing any kind of association that might exist from X1 to X0. So once I get that, how about we call then the corresponding residuals from this model X1, 0. So now I got two things where I have removed the effects of X0 from. Okay? E0 is Y without the effects of X0. X1, 0 is the effects of X1 without X0. Now that I have that, now I can just focus on testing gamma. And maybe we need to remember a big picture thing here. When you do, for example, if we think about it in a general setting, when you do a partial F test here for this gamma, what you're essentially saying is, given everything else is in the model, what's the effect of this X1? And so what we're doing here is we're removing the effect of then everything that's left in the model, this x0, so we can just focus on x1 itself. Okay. So now that I got this E0 and X1 0, now I can do this case-based resampling based upon these two things. Now remember how we did case-based resampling before when we just simply had one X and one Y. We simply randomly sample from the X's, we randomly sample from the Y's, form, let's say, a new vector of the data then, and put them together. That's what we're going to do here. I'm going to randomly resample from the E0s. I'm going to randomly resample from the X1 zeros, and then put them back together to form a new data set, estimate my model, get my estimated parameters under these resamples, and then I can proceed in a similar way to what we've done before to calculate p-values involving those parameters. We'll have an example coming up. Fortunately, though, it gets messier than this case-based resampling when we have a gamma that's not 1 by 1 anymore. So it's, in a very general sense, you can say p minus q by 1. You get your E0 exactly the same way as before. But the problem is getting this x1 0. Because what's happening here, this x1 0 is actually n by 1. The 1 comes from the fact that you're testing one variable. Now, x1 is n by p minus q. So if I want to remove the effect of x0 from x1, I need to actually do something in a multivariate class would be referred to as multiple regression. This is I'm using that term in a different way than how you normally think of it, like in the static semi-class. Now I'm doing basically, you can maybe call it multivariate regression, where now I have p minus q responses, and I have then all my explanatory variables in x0 itself. Essentially what it comes down to, at least when I talk about this in Stat 873, what it comes down to is simply for, let's say, your first variable that's in x1, fit a regression model with all the variables in x0. For your second variable in x1, fit a regression model with all the variables in your x0. You keep on doing that for all p minus q values in x1. Get the residuals from that, from each of those models. That's going to be our x1 0. In matrix form, you can actually find it rather simple through that equation there. Notice that this is a hat matrix involving the x0s. Okay. What do you use as a test statistic then? Well, use the usual old partial F-test test statistic. This is what I would use in Stat 870, for example. The residual sums of squares under the null hypothesis model. I see residual sums of squares from the full model divided by p minus q. All that divided by what ends up usually being your MSE. Residual sums of squares divided by n minus p minus q. Okay. Excuse me? I believe it's equivalent to a likelihood ratio under normality. Now in R, to do this partial F test, there's a function called ANOVA that makes it really simple. Okay, now let's take a look at an example. Hopefully this will clear up a few things if things are a little bit hazy right now. So this involves the rock data. from the book. The response variable is the permeability of these rocks, and they use the log, natural log transformation of it. And the explanatory variables are just three: area, the perimeter, and shape. There are actually 48 observations total in the data set. It's on page 282 of the book. And the 48 observations come from 4 different cross-sections of 12 core samples. So notice what we basically have here is we have a sample size of 12. We can say, to some respect, we have subsampling, because you're basically getting four values from each of the 12. And because of that, the authors are kind of concerned about then the correlation that would exist from the exact same sample. And so what they decided to do was actually find average values for each core sample, and actually then reduce the sample size to essentially 12 and analyze that. And so that's what we're going to do here. So here's the actual data, what it looks like. It's in the data frame rock. And I was just curious what would happen if I did actually estimate the model without reducing down to a sample size of 12. And so I actually just simply estimated the model, the log of permeability, tilde. Here are my 3 explanatory variables. I summarize the fit. I get hat matrix diagonal values. I get my standardized residuals as well. And then I do a plot. This is what I get. Standardized residual on the y-axis, core number on the x-axis. So again, what the authors were afraid of is that, based upon the same core, there's going to be this extra, there's going to be correlation between the actual observed values and stuff. And so what we see here for core 1, notice how the standardized residuals are all down here. Core 2, they're all around here, and so on. So we see what the authors were afraid of. We see this dependence based upon the core. There's a variety of ways in that you could actually handle that other than averaging over the 4 observations per core. One thing that I did just to quickly look at it was what happens if I included actually what ends up being a fixed effect for core as an explanatory variable in my model. So to actually get then the explanatory variable values, I create an object called core, and I use the ceiling function to help me get 1, 1, 1, 1, and 2, 2, 2, 2, and so on to correspond to the core numbers for every single observation. I do that for all 48. And since this is a numerical value, this value for core that I get, I need to tell R, don't treat it as a numerical value, treat it as a qualitative variable. Because whether you're in core 1 or core 2 is not necessarily greater than core 1. So I use the factor function to do that. I've never seen that before. And then I get my standardized residuals. This is what I get. So what do you think? Do you think this kind of takes care of this problem of this correlation within core? I think it generally does. So that could be another solution there. Perhaps we could, say core is a random effect too. Obviously we like to make inferences to the next core that comes out, and you could probably do a similar thing such as this. Okay, I'm going to jump over here now. Okay. Now so this is my entire data set. Oops. So this is my entire data set here. Again, 48 observations. Let me actually show you what it looks like with core in there. So I formed this rock 2 data set that has the core number. And what I need to do is basically average over these guys here, these four. Do it for the next four, do it for the next four, and so on. And note, the authors note this too, the permeability is actually the same for every single observation. It's just the explanatory variables vary for the, I guess, the different measurements that are happening across the board.
Quick question.
Yeah.
What is the shape exactly?
The shape of the rock.
Well, how is that numerical?
Maybe they fit a polygon, something
Okay.
around it.
Okay. It's
Did you read the book and hear what they said?
Interesting
read what they said?
numbers.
Anyway, I don't remember it from actually being said in the book what these represent. You know, sometimes in a class like this, we don't necessarily pay attention to exactly what these variables mean. We're interested in the statistics about it. If this was a non-statistics class, then we'd be very concerned about the shape of the rock. Anyway, so how can I condense the data down? I think the easiest way, and I didn't do this, I thought of this before class when I was reviewing my notes, so this is not in the notes. The easiest way would be to use the aggregate function, and I'm going to combine by column my four variables, and I want to basically average over. I want to average by core, and I'm using the function mean for every single unique core. My data is in rock 2, so this is what I get. There's my average data. What I ended up actually doing it in R instead was I used the G summary function. G stands for group, and then group summary. It's summarized by group. It's in the NLME package, nonlinear mixed effects. And I take my rock 2 data set. So what does it say?
The square root of perimeter divided by area.
Yeah, of course.
Exactly
But that was
how I
impressive
would
that you have your book here to look it up. Extra credit. You don't all have to get out your books, I'm just showing you guys. So I'm going to average over, and I'm doing it by core. So that's what my groups are, and I will get exactly the same result. But the aggregate function does it in one line of code versus 2. So this is on page 58 now. So next, let's actually estimate the model to this, what I call rock.small data set. Estimate it as you would expect. And we can see the area and perimeter are significant. And shape, though, is not. Again, these are t-tests that we see here. And remember what these t-tests represent in a regression setting. Given all the other variables that are in the model, let's test this one particular variable. And so for shape, it's not significant given the other variables that are in the model. And the authors want to focus, are actually going to focus in on the shape variable. We can actually estimate the model, the reduced model without shape, if we were going to do a hypothesis test for shape itself. And we can then use the ANOVA function to actually perform the test for us this way. This is just a very general way to do the test using a partial F test. And so here's my HO model without shape in it. And then I say ANOVA. I put my reduced model in first, then my complete or full model in second. Say test equal F for partial F test. And notice my p-value is exactly the same as we got above, because of course a t-test is equivalent to an f-test when we're testing the variable at a time. Okay, any questions so far about the setup? Okay, so page 59 now. The authors focus on the test of beta 3 is equal to 0 versus beta 3 does not equal 0. Let's do model-based resampling first for this situation. So the first thing I need to do, this is on page 660, is I need to estimate my model under HO. We already did this, but I just did it again to emphasize that we need to estimate the model under HO. I put then my estimated responses, what I was calling mu hat 0, I put that into mu.hat.ho. I also find my hat matrix diagonal values so that I can find my modified residuals under the null hypothesis model. Next, I write my usual calc.t-like function. I'm going to pass into the function the mean adjusted modified residuals. And since I'm just testing this out, I'm going to set my indices to be basically 1 to n. Pass in mu.ho and also my x values. Notice I actually pass in the whole data set because I have more than one explanatory variable. So here's my calc.t. It should look very similar to what we saw for that investment example. I get my epsilon stars up here. I find then my y star under the null hypothesis. So notice this mu.hat was actually passed in as mu.hat.ho. So these are my y stars again under the null hypothesis. I find a new data frame that contains my y stars and my original x's. Then I estimate my full or complete model. So notice how you have all the variables there. Look at the data set, rock.ho. Look at the response. So it says log.perm, but what it is actually, I've been calling it y star. It's actually log of y star. I summarize the fit, put the result in sum.fit so I can grab out then that corresponding standard error that I need to do my test involving the shape parameter and variable. I also pass back all my beta hats. So let's actually do the bootstrap. I save the results in boot.res.modbase. This is what I get. Notice there are 5 different things that are passed back. This involves the beta hat. This involves the square root estimated variance of beta hat 3. So we're testing the third x. Now the authors of our book, for some reason, they decide now to say, let's just do this as a one-sided test. So if we did this a one-sided test, and let's just say that we just did it with the beta hat itself. So what I have here in the fourth component of my $t part, this is beta hat star 3. I compare this to my observed beta hat 3 under the full model. And essentially I find the proportion of these beta hat stars greater than beta hat. I get 0.235. What would be a two-sided test p-dot here? If I just only use beta hats, I didn't use standardized, I didn't use the z's. Approximately 0.865. We have that greater than or equal to in there. And so it would be 0.47, which, again, is very similar to the 0.4878 that we got from the partial F test. Now we can also do this test then using our z's instead. So z0 again would be beta hat 3 minus 0 divided by the square root of the estimated variance of beta hat 3. That's going to be my z0. then my Z star then is essentially the same thing, but now I work with the star values. The usual way that we calculate a two-tailed test p-value, this is now using Z0, I get 0.494, which again is very similar to what we get using a regular linear distribution approximation. Okay. We can also do a little graphical summary, and so I do this at the Z stars, again using very similar code to what we've seen before. And this is what we get. I'm going to blow this up a little bit. It's on page 63. And you know what we see here, the red line is the normal distribution, where I simply use the mean of the Z star zeros and the variance of the Z star zeros. The dashed line is a t-distribution with 8 degrees of freedom, which would be normally what we would do in this particular setting. Be 12 minus 4, because we're estimating 4 parameters. And also we see the EDF plot too, and we can see that we're getting what we normally would expect if all the assumptions in the model were satisfied. Note that it might be a little bit misleading here to compare the t-distribution to this particular normal distribution, because typically you would say a normal 0, 1 you would actually compare it to. I just did the mean of the Z star zeros and variance of the Z star zeros. Okay. Are there any questions? Okay, let's do case-based resampling now. Again, this is more difficult, unfortunately. It also is a little bit more difficult in the sense of the boot function is not set up very well to do this. And I know when I was preparing for class today, I was thinking, maybe next time that I teach this course, maybe I should just write this up without using the boot function. And I think you'll see why it gets kind of messy. And we've seen this in other places this semester too, that when you do hypothesis testing, often using the boot function is not as convenient. It's just simply using, let's say, the sample function to sample the necessary indices that you need and just do all the coding yourself. But anyway, I chose to do the boot function here. But maybe next year, or next time I teach this, I'll do it a little bit differently. Okay, so here's what we need to do. The first thing is that we need to adjust out for the effects of the perimeter and the area, the area explanatory variables. So we need to adjust out for those two variables so that we can just focus on the permeability and also the shape. So I need to find E0 and then this x1 dot 0. So the first thing I do is I estimate now my model under the null hypothesis. We've already done this, but I'll just do it again here. My E0 is simply then the residuals from this mod.fit. That's it. This x0, easiest way to find it is just simply use the necessary matrix algebra. So what I'm doing here, a little split screen here just to emphasize. It's 53. So what I want to do is find basically this matrix. So, first of all, I find my x0 matrix. Maybe it's a little bit longer way than what I needed to do. But basically what I need is I need a matrix that looks like this. Column of ones, I need all the area values, and then I need all the perimeter values in there. So what I do is I find the area, I take that out of rock.small, I also find the perimeter value, take that out of rock.small, and I combine it all with a 1. And because R uses recycling, what it's going to do is repeat this 1 12 times to correspond to the size of area and perimeter. I put this all into a matrix, call it X0. Then remember here, this is essentially a hat matrix, so I call this H.0. And I find this hat matrix. I find now an identity matrix that's 12 by 12. An alternative way that one could have done this, I don't know why I didn't do this, it's just to say diag 12, and that would have gave me my identity matrix. Then I find a matrix, which ends up, in this case, just being a vector that has the shape variable in it. And in the end, I find my x.10, just putting the matrix syntax, or the matrix algebra into the correct syntax form. And I get a 12 by 1 vector. Now, if I was testing more than one variable at a time, so let's say I was testing both the shape and the, let's say, the perimeter, then this would have been 12 by 2. Okay? So please be aware of that. I also do some checking here. Let's say that I actually estimated a model that had shape as the response, area and perimeter as the explanatory variables, get the residuals out, and they are exactly the same as up there. So this would be, I guess, maybe this would be an easier way to do the x1.0. If you ended up actually having, if you were testing more than one variable at a time, again, if you were doing shape and perimeter, then your LM function would look like this. Use the cbind, shape, perimeter, tilde, area, and then do the rest. That's how you would have had two response variables to form this multiple or multivariate regression model. For those who've taken 873, do you talk about these kinds of regression models where you have more than one response? Sound familiar at all? Okay, I would assume since no one's saying yes, that means you don't do that. Yeah, it's usually when I discuss it, usually right at the end of the semester, and I don't really discuss it much, so maybe Ken doesn't do that either. Okay, so now what I need is I need to estimate then the corresponding parameter for using E.0, using our syntax here, as my response, and then also using X1.0 as the explanatory variable, because both these now have adjusted out this X0. So I could use the LM function again. Instead, I went back to basic principles and did the old x prime x inverse, x prime y. Now, in the terms of the what we have here for the, let's say, the X matrix and the Y matrix. And that's what I call my gamma hat. What this represents now is the estimate for gamma hat. In our original model, when we partitioned the model into two different forms, in terms of the full full model and the reduced model. Okay. Let's see. As you can see here, I have a lot of notes because I wrote my code here to be very general so that you could use these same ideas for if you were testing more than one variable at a time. And this is just some of the discussion about that. I'll hit on the main points as we go along. Okay. in order to do the resampling, of course, I'm going to have to write a calc.t function. Now, if you remember, when we did case-based resampling, when we had just one y and one x, remember what we did? We randomly sampled from the y's, we randomly sampled from the x's, and as kind of a trick, in order to get the boot function to do it, we would create a data frame that had, let's say, all the y's and then all the x's. And then we would have a label column that said, okay, these are my y's, these are my x's. And then I use the boot function with the strata argument, where I'm stratifying by this label, so that I can independently resample the y's, independently resample the x's. I need to do exactly the same thing here. Essentially, I should say the same thing. But I do this a little bit differently so that you can generalize this code to the situation where you would have more than one variable you're testing at a time. So I created a data frame called set1. In this data frame, I have the E0 and I have my label. So essentially what I did was this part right here. Next, what you might think that I do here is now I put my x1.0 in there. But what if x.10 was actually was accounting for more than one variable? In that case, then, this x.10 might be, let's say, n by 2 or n by 3. But this e.0 is n by 1. And you can't configure everything in a data frame in the right way. So what I decided to do was put a dummy value. And I just said, how about we repeat 1 n times, label it dummy, and put it in there. So what I have here in the set one, and I guess we can take a look at the whole thing to make sure it's clear. So here's set one. Remember, our data set has a size of 12, and so we see we have 24 items in there. And what this is essentially going to let me do then is when I say do this stratified resampling, I'm going to get indices for this part right here. But I'm not going to pull out those ones because those are just dummy variables. But what I will have is the indices that will help me then resample x1.0. So let's take a look at that code then. So calc.t.cases. I'm going to pass in my data, which is going to be set 1. R is going to pass in indices, stratified resampled indices. I'm going to pass in my actual x1.0. The reason why I do this is because what happens if it's more, it has more columns than just one. And then my sample size itself. So when I say D gets data I there, excuse me, just my usual, I get my usual data, you could say, rearranged, and then I pull out my E0s. So notice here for the rows, I'm only looking at the E0 ones. For x10 then, look at how I use my I. I look at the n plus 1 to the 2 times n different I. Because remember, these correspond to the dummy values. I subtract off n because I want to shift the indices down by n. So remember, I have 24 items actually in my data. So that's why the n gets, the indices will be n higher than what I want them to be, so I subtract off n. And this is how I pull out my x10. I estimate gamma. I get my residuals from that fit. I use those residuals then to form what essentially is a MSE. Also, I get a covariance matrix, and I pass back gamma and the corresponding variance for this gamma. So I run my boot function, stratified resampling. What comes back then is my gamma hat stars. Here's my observed value of gamma hat. And if I do a one-sided test, I get a p-value of 0.201. Before, for a one-sided test with model-based resampling, we got 0.235, which is on page 661. If I do work with a standardized quantity instead, I get a p-value of 0.402. And again, before what we had found was 0.494. So it's kind of close. And so that's how you do the case-based resampling. Obviously, again, it's a lot more involved. It is a lot more involved. And based upon the looks that I'm getting from some of you, I strongly recommend what you do is just run through it line by line by line so you can see exactly what's going on. Because to some respect, in these situations, this kind of code is hard for me to explain as fully as I would like in the class, in the classroom setting. So please run through it line by line. If you have questions, then bring them next time or post them. Are there any questions about this? Okay. Why don't we end it there today? And we have one more section of Chapter 6 left to do.